Alright, today we're going to talk about light waves, and particularly the electromagnetic spectrum. And this is PS9, and you're going to investigate and understand characteristics of transverse waves. So our essential questions at the top of your notes is, what is the electromagnetic spectrum? And down below is an example of the electromagnetic spectrum. And this includes everything from radio waves, to microwaves, to visible light, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. So this is the spectrum, and you can notice down here there's a wavelength, okay, and as we get closer to the gamma rays, the wavelength is shorter, so your frequency gets higher. And so we're going to talk more about each part of it. Okay, the first thing you need to know is electromagnetic waves travel perpendicular, okay, to both electric and magnetic fields. So they actually interact with electric and magnetic fields. Light waves are a little different than other kinds of waves. They're electrically charged particles that are going to vibrate to produce an electromagnetic wave. Okay? And so light waves are vibrating electric and magnetic fields that transfer energy through space. These are the waves that can actually go and travel through empty space. They need no medium. Unlike sound waves, which needs a medium, sound waves needs a solid liquid or gas, light waves do not. So, electromagnetic waves, I'm going to give you a little animation how they form. So here is the electromagnetic field, and there's electric field there going up and down, and a magnetic field going there. And this is how a light wave kind of travels through space. Okay, it goes up and down. It's a transverse wave, and also goes side to side. Okay, so unlike a longitudinal wave, okay, light waves go up and down. Alright, so our question is, what is the nature of light? And radiation is energy that has been transmitted by wave or particles. This transfer of energy is called EM radiation, or electromagnetic radiation. So all light is electromagnetic radiation. And these waves move at the same speed in a vacuum, okay, the speed of light. So it doesn't matter if it's a radio wave, if it's a ultraviolet wave, infrared, light waves, visible light waves, they all move at the speed of light. Okay? And they can travel through many materials. So sound can't travel through space, but these can travel through space. They can travel through gases. They can travel through different other materials that light can pass through. Okay? So different frequencies of electromagnetic waves carry different amounts of energy. So higher frequencies have more energy than low frequencies. So that means the gamma rays over here, who have shorter wavelengths, have a lot more energy than the radio and the microwaves and infrared, which have a longer wavelength. So the big thing here to understand is longer wavelengths, okay, lower energy, shorter wavelength, higher energy. So what determines the color of light? So there's only a really small area of spectrum, really small narrow part of the electromagnetic spectrum that's actually visible to us. We can only see this part, the red, orange, yellow, green, blue, indigo, and violet. Okay, so we call it Roy G. Biv. And white light is what we perceive when we see all the wavelengths of light at once in equal proportions. So our eyes only register 3 colors of light, by the way. It's red, green, and blue. And all the colors we see is a mixture of these 3 colors. Okay. So the range of frequencies that electromagnetic waves can have is called the electromagnetic spectrum. And right here, we talk about visible light. This is the only part of the whole spectrum that we can actually see. We can't see ultraviolet light. We can't see infrared radiation. Okay, we can only see this right here. Now, infrared light is slightly longer wavelength than red light. Okay? And ultraviolet has a slightly shorter wavelength than violet light. What that means is infrared would be beyond, okay, red. It'd be on this side, and ultraviolet would be shorter wavelengths. It'd be beyond violet over here on this side. Most of the sun's energy is in the narrow visible light range, but the sun gives off some radiation in every part of the spectrum. Okay, so most of the energy of the sun's giving off is in that very small area, the visible light. Not all wavelengths of light can penetrate the atmosphere. Radio waves penetrate the atmosphere easily. The ones that are actually harder to penetrate are some of the gamma rays. They don't really penetrate very easily. Here we go. So how much of the sun's radiation reaches us? Some of the electromagnetic radiation can be dangerous to humans, so we take extra steps to protect ourselves. What that means is the ultraviolet, X-rays, and gamma rays, these down here, these light rays, are much stronger, and so we have to make sure we take protection against us. If it's ultraviolet, we still get ultraviolet from the sun, but you put sunscreen on. X-rays, you wear that lead vest, and usually we don't use gamma rays unless you're undergoing some type of cancer or radiation treatment in the hospital. So in space, the dangers of electromagnetic radiation are very high because there's no atmosphere, there's nothing to protect us from those. Different frequencies of electromagnetic waves can carry different amounts of energy. Okay? So high frequencies have more energy than low frequencies, like we talked about earlier. So because of that, low frequency waves such as radio waves carry less energy, and they're much safer for us to use. So we use these for like walkie-talkies. You might use them for your car radio. Those are radio waves, and they're actually traveling at the speed of light through our atmosphere to your car or the radio or whatever. Now high frequency waves such as ultraviolet light carry more energy and can be harmful. So UV light causes sunburns. X-rays require more protection like that lead vest we talked about. And here's a really quick video that I want you guys to watch. So I need you guys to zero in on this, take the QR code, scan it. If not, you can go to the website and click on the electromagnetic spectrum link. Alright, the other part of the class today is you're going to be exploring with white light, and what you're going to do is you're going to actually use a prism to bend the white light, like sunlight, into the multiple colors we see here. And I want you guys to find out, why do you think reds, okay, the red over here doesn't bend as much as the violet, the blue, and the indigo. These ones bend more than those ones. So we call that refraction, and we're going to talk about that a little bit later. Okay, so these are materials you're going to be using later on in your experiment. Okay, and I'm going to click out, and we're going to go to this. This is our laser beam, and we're going to use the white light, and we're going to use a prism. And when you see the prism there, you notice that the light bends. It actually, as it travels through the glass prism, it bends there. And the blues bend a lot more than the reds. So the reason for that is it's all about the frequency and the wavelength. Okay? So if we go back here, okay, to our PowerPoint, you'll see that the purples bend, and the violets and the blues bend more than the reds. That's because the wavelengths are longer than the reds and the oranges, so they don't bend as much. Okay? The ones that have a shorter wavelength, the light that passes through has shorter wavelength, it starts to bend more, and that's how we get to see that. So the white light is a mixture of all the colors, but once it goes through the prism through a different medium, okay, so light can go through other mediums, okay, but it bends less if it's a longer wavelength and more if it's a shorter wavelength. Okay, that's all we have. When you guys are going to switch places and do this lab on the computer, or you can actually use the real prism.